From ancient ambition to modern precision, this film explores how colossal canals are engineered, carved, and controlled, revealing ingenuity that reshapes landscapes and connects civilizations. The Leviathan project represents one of the most ambitious energy ventures in Israel's history and a landmark achievement for Noble Energy and its partners. Discovered in 2010, the Leviathan gas field holds some of the largest recoverable natural gas reserves in the eastern Mediterranean, fundamentally transforming Israel's energy landscape and regional role as an energy supplier. Early in the development phase, drilling operations targeted key subsea wells, including the drill Leviathan No. 3 well, which helped unlock the reservoir's vast supply. A major flow test at Leviathan 7 well confirmed stable gas flow, paving the way for downstream infrastructure work that would connect the field to market. Throughout construction, meticulous installation sequences took place, from tree installation on subsea wells to pipe manufacturing and pipe installation across the seabed and shore crossing. Umbilical manufacturing and installation ensured reliable control systems for remote subsea equipment. Simultaneously, key structural components were assembled and floated into position. This included a cellar deck, production deck, and main deck floats that formed the offshore production platform. The platform jacket underwent roll-ups, jacket launch, and sail-away operations before being secured in place with pile installations. Onshore, the door valve station was built to regulate gas flow into the national grid, and the LSM sail-away marked the final major module departure toward its offshore destination. Following years of drilling, construction, and assembly, the Leviathan project achieved a historic milestone when natural gas flowed for the first time in December 2019, beginning commercial production and delivering gas to Israel and neighboring countries. This first gas marked a turning point in the region's energy security, enabling Israel to reduce reliance on imported fuels and become a major exporter of natural gas. The Kachhi Canal project is designed to transform agriculture and livelihoods in the arid regions of Balochistan by delivering reliable irrigation water from the Indus River. Under this project, the Kachhi Canal offtakes from the Tonsa Barrage, located on the Indus in Punjab province. From this strategic intake point, the canal conveys water southwestward toward the vast Kachhi Plain. Before entering Balochistan, the canal runs parallel to several existing and planned irrigation channels, including the DG Khan Canal, the Dajjal Branch, and the proposed Dajjal Branch extension. For nearly 300 kilometers, the Kachhi Canal follows these waterways on their right-hand side, demonstrating careful alignment planning to optimize land use and hydraulic efficiency. Within Balochistan province, the proposed length of the main Kachhi Canal is approximately 220 kilometers. Once completed, the project will irrigate about 713,000 acres of cultivable command area, bringing water to land that has long depended on uncertain rainfall. Importantly, the canal is dedicated exclusively to providing irrigation facilities within Balochistan, addressing long-standing regional water needs. As shown in the video, extensive earthwork operations carried out by Ramzan and Sons form the foundation of this ambitious scheme, marking a crucial step towards sustainable agriculture, economic growth, and improved food security in the region. The Kachhi Canal project represents a major irrigation development aimed at transforming arid land into productive agricultural areas. In this section of the project, construction activities focus on shaping, strengthening, and protecting the canal to ensure long-term efficiency and durability. The process begins with extensive earthwork, where large volumes of soil are excavated and leveled to form the canal bed and embankments. Once the basic canal profile is established, slope trimming is carried out to achieve precise gradients and stable side slopes, which are essential for smooth water flow and erosion control. Next, canal lining operations are performed. Concrete lining is applied to the canal bed and slopes to minimize seepage losses, improve flow efficiency, and reduce maintenance requirements. Special attention is given to structural components such as the superpassage, which allows natural drainage or roads to safely cross over the canal without disrupting water flow. In addition, the construction of the wing walls of the distributary provides structural support and directs water effectively into branch channels. Throughout the project, repeated stages of earthwork and lining ensure accuracy, strength, and proper alignment. Overall, the coordinated execution of earthwork, lining, slope trimming, and structural works demonstrates the engineering precision behind the Kachhi Canal project, contributing significantly to regional water management and agricultural development. The Kachhi Canal project is a major irrigation infrastructure initiative designed to restore and strengthen one of the most important water channels in the region. The project scope covers the restoration of embankments and the rehabilitation of both IP and NIP sections to ensure long-term structural stability. Extensive filling of rain cuts is carried out to repair erosion caused by seasonal rainfall and to prevent further damage to the canal body. In addition, damaged RCC railings along the canal are replaced to improve safety and durability, while deteriorated PCC lining sections are renewed to enhance water flow efficiency and reduce seepage losses. These works are implemented continuously from RD0+000 to RD106+000, covering a significant length of the canal. Overall, the project plays a vital role in improving irrigation reliability, protecting canal infrastructure, and supporting agricultural productivity in the Kachhi Canal command area. The project begins with Phase 1's subgrade preparation, which forms the foundation for all subsequent works. During this stage, the ground is cleared, leveled, and compacted to achieve the required bearing capacity. Proper subgrade preparation is essential to prevent settlement and to provide a stable base for future structures and pavements. Following this, L-shaped drainage systems are installed across the site. These drains play a critical role in managing surface water and preventing water accumulation, especially during heavy rainfall. The installation ensures effective water flow control and protects the subgrade from erosion and moisture-related damage. Next, mass excavation is carried out in Phase 1. Heavy machinery removes large volumes of soil to achieve the designed ground levels. This process prepares the site for infrastructure networks and building foundations. The project then advances into Phase 2 mass excavation, expanding earthworks to additional zones of the development. This phase further refines the site layout and accommodates future industrial plots and road networks. Finally, filling works are performed using selected materials. The excavated areas are backfilled and compacted in layers to reach final formation levels. This step ensures ground stability and readiness for the next stages of construction. Overall, the systematic execution of subgrade works, drainage installation, excavation, and filling highlights the project's commitment to quality construction and sustainable industrial development at More Furniture City. The Sheikh Jabr Al Ahmad Al Sabah Causeway is one of Kuwait's most ambitious and iconic infrastructure projects, spanning the Bay of Kuwait and redefining connectivity across the country. Designed as a dual-direction causeway, the project consists of two major links. The main link, connecting Kuwait City with northern Kuwait, including Subsea and Bubiyan Island, and the Doha link, which connects Kuwait City to the Doha district. Together, these links significantly reduce travel time, support urban expansion, and strengthen economic integration between key regions of Kuwait. Structurally, the causeway is designed in accordance with standards set by the American Association of State Highways and transportation officials, ensuring high levels of safety and durability. The most striking feature of the main link is its cable-stayed bridge, crowned by an iconic pylon, inspired by the shape of a traditional sailboat, a powerful symbol of Kuwait's maritime heritage. Rising approximately 151 meters, the pylon reaches a height comparable to the famous Kuwait Towers, making it a defining landmark on the skyline. To accelerate delivery, the project was divided into two contracts, the 36.14-kilometer main link and the 12.4-kilometer Doha link. The causeway represents a truly global collaboration involving leading engineering, design, and construction firms from the United States, Europe, and Asia. Major contributors included Hyundai Engineering and Construction, GSE&C, AECOM, Sistra, TY Lin International, and Tony Gee and Partners, supported by specialized suppliers and consultants. Environmental protection was a key priority from the very beginning. Special measures were implemented to minimize impacts on marine life and natural habitats. Notably, green tiger shrimps native to Kuwait Bay were safeguarded through the creation of artificial reefs and new vegetation zones away from construction areas. These efforts proved highly successful, with shrimp populations thriving and reproducing abundantly. Overall, the Sheikh Jabr Al Ahmad Al Sabah Causeway stands as a symbol of engineering excellence, cultural identity, and sustainable development in Kuwait. The canal side stone patching technique is an essential maintenance method used to protect and restore the banks of irrigation and drainage canals. In this process, damaged or eroded sections of the canal slope are first identified and carefully cleaned to remove loose soil, vegetation, and unstable stones. After surface preparation, workers reposition existing stones or place new natural stones to rebuild the canal lining. These stones are arranged tightly to ensure proper interlocking and structural stability. Mortar or cement slurry is then applied to fill gaps between stones, improving bonding strength and preventing water infiltration. This patching technique helps resist erosion caused by flowing water, rainfall, and seasonal fluctuations in water levels. Moreover, it extends the service life of the canal while reducing the risk of slope failure and leakage. Overall, canal sidestone patching is a cost-effective and durable solution for maintaining canal safety, hydraulic efficiency, and long-term operational performance. The water supply operation for the Sheikh Zayed Canal begins with Nile water being pumped from Lake Nasser through the Mubarak pumping station into the canal system. This carefully engineered canal, part of the larger Toshka/New Valley development project, transports water across the western desert to irrigate vast agricultural lands and support new rural development. Water flows under the newly constructed Toshka Bridge, marking a key milestone in delivering irrigation water to remote fields. The flow is controlled and monitored to ensure steady distribution, overcoming natural elevation differences. This operation enhances irrigation efficiency, helps transform desert regions into productive farmland, and plays a vital role in Egypt's national development goals. The construction of Paradise Farm in the Karbala Desert represents an inspiring transformation of an arid and challenging landscape into a productive agricultural oasis. Located in a region known for extreme temperatures, scarce rainfall, and sandy soil, the project demonstrates how modern engineering and sustainable planning can overcome harsh desert conditions. The development begins with extensive land preparation, including leveling, soil stabilization, and the construction of access roads to support heavy machinery. Deep wells are drilled to secure reliable groundwater sources, while advanced irrigation systems, such as drip and pivot irrigation, are installed to minimize water loss and maximize efficiency. At the same time, windbreaks and protective fencing are built to shield crops from sandstorms and desert winds. Soil improvement plays a critical role, with organic matter and nutrients added to enhance fertility. Greenhouses, storage facilities, and service buildings are then constructed to support year-round farming operations. Through innovation, careful resource management, and determination, Paradise Farm stands as a symbol of hope, proving that life and agriculture can flourish even in the heart of the desert. Techcross Water and Energy is a leading global EPC company delivering integrated water treatment, energy conversion, and sustainable environmental solutions worldwide. Drill pipe connections are a routine yet highly critical task, as they allow the drill string to extend deeper into the earth while maintaining strength, alignment, and the ability to transmit rotation and drilling fluid. The process begins when the drilling operation is temporarily paused and the rotating drill string is held securely in place by slips at the drill floor. A new section of drill pipe is then lifted from the pipe rack using the hoisting system and guided vertically into position above the existing drill string. Precision at this stage is vital, as even small misalignments can damage the threads or compromise the connection. Next, the lower end of the new drill pipe is carefully aligned with the box end of the pipe already in the well. Once aligned, the pipe is slowly lowered until the threads engage. The connection is first made up by hand to ensure proper thread engagement and to prevent cross-threading. This initial step helps protect the integrity of the pipe and ensures a tight, reliable joint. After hand tightening, powered equipment such as a spinning wrench or iron roughneck is used to rotate the pipe and tighten the connection further. The final tightening, known as torquing up, applies a specified amount of torque to ensure the joint is secure and capable of withstanding high loads, pressure, and vibration during drilling. Correct torque is crucial for preventing leaks, connection failure, or pipe separation downhole. Once the connection is completed, the slips are released, and the drill string is lowered back into the well. Drilling operations then resume, with the newly added drill pipe extending the reach of the drill bit deeper underground. This repetitive but carefully controlled process continues until the desired drilling depth is achieved. Overall, the drill pipe connection process demonstrates the importance of precision, teamwork, and safety in oil rig operations, ensuring efficient drilling while maintaining structural integrity and operational reliability. The bridge installation project in Walperskirchen stands as an impressive demonstration of modern civil engineering and Bavarian construction expertise. Following the demolition of a historic bridge that had reached the end of its service life, a completely new reinforced concrete bridge was prepared to take its place. Instead of being built directly over the obstacle, the new structure was constructed nearby and later moved into its final position using an advanced bridge launching method. This approach minimized disruption, improved safety, and showcased precise engineering control. The newly built bridge is a massive reinforced concrete structure weighing approximately 400 tons. Due to its enormous size and weight, conventional lifting methods were not feasible. Instead, engineers chose the incremental launching technique, also known as bridge pushing. This method involves sliding the bridge horizontally into position using powerful hydraulic systems, allowing the structure to be installed accurately and efficiently within a very limited time window. Before the launch could begin, extensive preparatory work was required. After the old bridge was carefully dismantled and removed, the gap it left behind was precisely measured and prepared. The abutments and foundations were inspected, adjusted, and reinforced to ensure they could safely receive the new load. At the same time, sliding tracks and steel plates were installed to reduce friction during the movement of the bridge. Special bearing elements were also positioned to guide the structure and keep it aligned throughout the process. The bridge itself was constructed on a temporary support platform adjacent to its final location. This allowed concrete curing, post-tensioning, and quality inspections to be completed under controlled conditions. Once the structure reached full strength, engineers began installing the hydraulic pushing system. A series of synchronized hydraulic cylinders was placed behind the bridge, designed to apply steady and evenly distributed force during the launch. When the bridge launching operation commenced, the hydraulic cylinders pushed the structure forward in small, carefully controlled increments. Each push moved the bridge only a short distance, after which the system was reset and checked before continuing. This step-by-step process ensured maximum precision and prevented unwanted stress or deformation in the concrete. Sensors continuously monitored movement, alignment, and load distribution, allowing engineers to react instantly to any irregularities. As the 400-ton bridge slowly advanced, it slid smoothly over the prepared surfaces and into the empty span once occupied by the historic bridge. The operation required absolute coordination between engineers, technicians, and machine operators. Even slight deviations in alignment could have caused significant problems, so constant communication and real-time data analysis were essential. Despite the complexity of the task, the bridge moved steadily forward, demonstrating the reliability of modern hydraulic technology. Once the bridge reached its final position, the pushing operation was halted, and the structure was gradually lowered onto its permanent bearings. These bearings are designed to accommodate temperature changes, traffic loads, and long-term structural movement. After final alignment checks confirmed that the bridge sat exactly as designed, the hydraulic systems and temporary sliding equipment were removed. The final phase of the project involved securing the bridge permanently and completing finishing works. This included sealing joints, installing safety barriers, applying road surfacing, and integrating drainage systems. Engineers also carried out detailed inspections to confirm that the structure met all safety and performance requirements. Only after these checks was the bridge declared ready for service. The successful bridge installation in Walpertskirchen attracted admiration far beyond the local region. The smooth execution of such a technically demanding operation highlighted the high level of planning, precision, and craftsmanship involved. It also demonstrated how modern construction methods can preserve infrastructure efficiency while minimizing environmental and traffic impact. In conclusion, the bridge launching operation in Walpertskirchen represents a remarkable achievement in reinforced concrete construction. By pushing a 400-ton bridge into place using hydraulic cylinders, Bavarian engineers showcased innovation, reliability, and technical excellence. This project not only replaced an aging structure, but also set an inspiring example of how advanced engineering solutions can meet complex challenges in modern infrastructure development. The third Bosphorus Bridge, officially known as the Yavuz Sultan Selim Bridge, represents one of the most ambitious infrastructure projects in Turkey and a landmark achievement in modern bridge engineering. Constructed between March 2015 and March 2016 as a core component of the Northern Marmara Motorway project, the bridge was designed to connect the European and Asian sides of Istanbul while carrying both highway and railway traffic on a single deck level. Combining advanced engineering, large-scale marine operations, and innovative construction techniques, the project stands among the world's most remarkable hybrid bridges in terms of size, capacity, and aesthetics. construction activities accelerated significantly in March 2015. One of the major milestones during this period was the rapid progress of the tower legs on the Asian side, which reached a height of 304 meters above sea level. These towers would later become the tallest bridge towers in the world at the time of completion. Simultaneously, the assembly of a massive derrick crane with a lifting capacity of 1,000 tons was successfully completed. This crane played a crucial role in handling extremely heavy steel components during deck installation and testing phases. Another major operation in March 2015 involved the transportation and installation of steel deck segments. The third steel deck section, weighing 940 tons and measuring 24 meters in length and 59 meters in width, was transported by a giant floating crane with a capacity of 1,800 tons. After being carefully lowered onto land, this deck segment underwent lifting tests using the 1,000-ton derrick crane to ensure structural integrity and lifting safety before final installation. Around the same time, the 8th steel deck segment, identical in weight and dimensions, was also successfully assembled, marking steady progress in deck fabrication and erection. In parallel with deck operations, the installation of inclined stay cables began. These cables form one of the two main load-bearing systems of the bridge, the other being the suspension cables. The initiation of stay cable installation marked the transformation of the project from foundation and tower works into a full-scale superstructure construction phase. Meanwhile, progress continued on the Northern Marmara motorway, where reinforced concrete works on the European side E2 section reached 51% completion at the V17 piers. One of the most critical stages of the bridge project was the preparation for the installation of the main suspension cables. To enable this, the construction of the catwalks, known locally as Kidi Yoleri, was completed. These temporary suspended walkways provided safe access for workers and equipment during cable spinning operations. Following the completion of the catwalks, saddle structures were installed on top of both towers, one on the European side and the other on the Asian side, allowing the main cables to pass smoothly over the towers. With all preparatory works completed, the spinning of the main cables began simultaneously from both shores of the Bosphorus. This operation required exceptional precision and coordination, as thousands of individual steel wires were pulled across the strait and assembled into massive cable bundles. Upon completion, a total of 71,645 kilometers of steel wire had been installed, forming the two main suspension cables that would carry the enormous loads of the bridge. After the cable spinning process was finalized, the main cables, initially hexagonal in shape, were compressed into a circular form. This compaction process increased structural efficiency and durability. The cables were compressed to a final diameter of 723 millimeters and securely fixed with steel bands. By this stage, the installation of inclined stay cables was also approaching completion. Approximately 500 kilometers of stay cable had already been pulled, demonstrating the immense scale of the project. As construction advanced toward the end of 2015, significant changes were introduced to improve efficiency. A new method was adopted for placing the steel deck segments. Instead of earlier lifting techniques, sliding cranes with a carrying capacity of up to 3,000 tons were introduced. These cranes lifted deck segments composed of two parts with a combined weight of 380 tons, enabling faster and safer installation. By this time, 42 steel deck segments had been fully installed and welded, leaving only 391 meters before the European and Asian sides would meet at the center span. By December 2015, the bridge structure had taken on its final form and finishing works accelerated. In January 2016, the installation and welding of the 41st and 42nd steel deck segments were completed, bringing the total number of installed segments close to the final count of 59. Each segment was aligned with millimeter-level precision and permanently welded to ensure continuity and strength across the entire span. In March 2016, works continued following the completion of cable installation. The two main suspension cables, with a combined weight of approximately 13,000 tons, entered the final coating phase. This protective coating was essential to shield the cables from corrosion caused by wind, moisture, and the harsh marine environment of the Bosphorus. At the same time, the inclined stay cable installation reached the end of its first phase. Approximately 600 kilometers of cable had been installed, and 160 stay cables were fully mounted, stabilizing the deck and distributing loads effectively to the towers. The final phase of the project also included infrastructure and safety installations on the northern Marmara motorway. On the European side E2 section, pedestrian railings and vehicle safety barriers were installed at the V19 piers, ensuring compliance with international safety standards. These works marked the transition from heavy structural construction to operational readiness. By March 2016, the third Bosphorus Bridge had emerged as a masterpiece of professional engineering and advanced technology. Designed to carry 8 lanes of motorway traffic and 2 railway lines at the same level, the bridge set new standards in hybrid bridge design. Its elegant silhouette, combined with outstanding structural performance, positioned it among the most important bridges in the world. The successful completion of the project within a single year stands as a testament to meticulous planning, innovative construction methods, and the coordinated effort of thousands of engineers, technicians, and workers.